We have to get started. Okay, it's not quite in the top of my head, but the point is, there's some two-component link with a term, which is this n.
Yeah.
That has the property that each component is then another circle by itself. So
it's your turn because you want
this round, the other one has a reasonable line.
and this
Would you make the other one round?
No.
That is the second one. It takes more atoms than the first to draw it. I mean, it becomes exponential. It's related to topology.
Okay, so we'll get started with the last session. The speaker is Xiaosheng Lu on topological crystalline insulators.
Yeah. Okay, thanks. I'm really honored to give a talk here, so everyone can hear me, and also thanks that it's late today. Okay. Hi. So everyone can hear me? Okay. So it's very late today. I'm thanks for everyone still here to listen to my talk. And so today what I want to talk about is about the topological crystalline insulator and the topolomagnetic crystalline insulator. So it's about the free fermion. I'm from Penn State University, and here is my my student and the collaborator. And here is the reference. So this is the outline of my talk. So first I will give a short introduction, since here most are expert about the topological insulator, and then I will talk about what does it mean about the topological crystalline insulators, and then I will briefly review the symmetry induced by symmetry induced degeneracy and how it's related to surface state. And then I will try to generalize it to different type of topological crystalline insulators and also topological magnetic crystalline insulators. Finally, the summary and the outlook. So I think there's a lot of talk in this There's a lot of talk in this workshop about the interaction system. So here, mainly I focus on is about the free fermion system. And we know that usually from the band theory that all the states, usually we can classify it into a method and the insulators determined by the Fermi energy in the band gap, or it's across some bands. And so the topological state of matter, so here mainly we focus on the Can you hear me? Okay. So here we mainly focus on the topological phase of the free fermions. So the most important example we know that is the contour state, that the bulk state are localized, but we have the chiral edge state that it only goes in goes along only one direction at the edge, and so when you Fermi energy in the bulk gap, you will have that all the transport is dominated by the edge state. Okay. And the recent development we know is that about this time-reversal invariant topological insulator. So the contour state, we know that it breaks time-reversal symmetry. And I think this is, there's a lot of talk about this already. And so here, basically, these are two copies of contour state, and for spin up, it's going one direction, and for spin down, it goes other direction, and in the bulk, it's also gap. Okay, and so one thing one can see that this edge state usually we call it helical edge state, and one important thing is that these two states are different from contour state that it only go in one direction. For here, these two states it will go in opposite direction and it will cross at some point. And of course, the question is that why this crossing will not be open gap? It will become anti-cross and open gap, and we know that the reason is that because of time-reversal symmetry, and that forbidden this gap opening. And so this is first. The quantum spin-Hall state has, so this topological insulator, time-reversal invariant topological insulator state has been observed in the experiment basically this helical edge or surface state. So this is the first experiment in the magnetized quantum wells, which shows this 2e2OH conductors. And then in three-dimensional, people can observe, use the APAS method, experimentally people can observe this surface state and show this there's this crossing point here. It's diacom and very nicely. Okay. And of course, one understanding that why here we know that this is degeneracy, and this is coming. Why this time-loss symmetry can preserve this degeneracy? We know that it's coming from this very important theory in condensed matter physics also, and it's this called the Kramer's degeneracy Kramer theory. So basically, it tells you that for the spin-4 fermions, and we have the spin up and the spin down state, they will be degenerate at this spin up state at k, they will be degenerate with the spin down state at the momentum minus k. So basically this state and this state will be degenerate. And of course spin up, spin down, they are different states. Then when you look at the time reversal invariant momentum, basically it's the in one dimension, in 1D, it's the k equal to 0 or k equal to pi. These two momentum, we know they are degenerate. And so why this state? So now we are talking about the surface state. So basically, why this degeneracy? It can protect some very non-trivial surface state. So we can look at this picture. Okay. So basically, now we are. So here, these are band gap. And so now if you look at the surface state and assume this k equal to lambda and the k equal to lambda a and lambda b, they are two time reversal invariant points. So you need to satisfy the time reversal, the Kramer theory. And that means that the all state at this point and at this point, they must be double degenerate. And so then you can draw this line, and then you will find there are two possible ways to draw this line for the state in the band gap. So basically, this you can draw all degeneracy point here and the degeneracy point here. They are drawn with the same band. Or here you can switch the band. So basically, they switch this pattern for the degeneracy here and the degeneracy here. And in this case, we know that it's actually it's just a trivial surface like the dangling bound we found. So because now you can imagine that you can add some potential on the surface, and then you can basically the potential on the surface state will change this. Well, maybe it will increase the potential here, and then you can move all this state to the conduction band. And but for the state here, you can also add some potential on the surface state. It will not influence the bulk band, but it will move the surface state up. But when this surface move up, and there will another band will put up from this valence band. Okay, so this is why we can understand that this surface state. We say that once this degeneracy is here, so you cannot remove it. Okay, this is why this surface is protected by the here. Of course, it's protected by time reverse symmetry. And from this picture, you can immediately realize that, so if we can find some degeneracy here, which is not protected by time reverse symmetry, but protected by some other symmetry, then we can, if we can construct some model which is similar to this type of surface state or edge state, then this, we know that it will robust once you keep this symmetry. Okay, so this is the main point here, that also the main point of how we try to generalize this one and to the crystalline symmetry. Okay, and so now next, so the idea is that what is topological crystalline insulator? So it's just like what you found for topological insulator. So it's bulk insulator in the bulk, and there's some edge or surface state at the there's some gap mode at the surface, and this surface state now is not protected by the time reverse symmetry, but protected by some crystalline symmetry. So this is basically the topological crystalline symmetry. And so, of course, the question is that is that type of surface state possible or not? So this is the work from the Liangfu group, and this shows that this is indeed possible. So basically, some gapless edge or surface state that's protected by the crystalline symmetry. And he basically found that this material, this tin telluride material, and you can find some surface state from this. This is from the AB initial calculation that they can find some surface state, and this surface state there will be crossing at some point, and this degeneracy they are due to some crystalline symmetry. Here is the mirror symmetry. Okay. And of course, one question is that whether or not this can be really observed in the experiment, because we know that usually in the crystal system, the crystal symmetry is some approximate symmetry because you have disorder, this type of thing. So people, in the early time, people question whether or not it really can be observed in experiment. And then people doing the APAS on this material, and they really observed for that's actually in 2012, and they really observed this surface state, and you can see a nice Dirac here, the same as what the theory predicted. And the people recently, there's some experiment, and the people can even show that when you control the crystalline symmetry, like control one direction mirror symmetry, you can gap some Dirac but preserve some other Dirac which we protect. Because for this crystal there are two mirror symmetries, so there are 4 Dirac which you can protect it by different mirror symmetry, and they can. No, just one, but there are 4. 2 are protected by one mirror symmetry and 2 protected by another. So they can basically they can gap the 2 by break one mirror symmetry, but they will find another 2 is still gapless. Yeah. Okay. So basically here is that this state really you can observe it, and also you can even control it by control the crystalline symmetry of the system. Okay. So here what we want to talk about here is that. Because we know that the crystal symmetry, they are if you look at crystal, there are space group, there are 200. In 3 dimensions, there are a lot of space crystal symmetry space group. So why not we can find a practical way and a systematic way to identify which type of crystal symmetry that is able to protect the non-trivial surface state. Okay. And so there are a bunch of work in the early time, but most of these work are usually try to identify bulk topological invariant based on bulk symmetry directly. But there's one problem here, because we know that when you look at the crystalline symmetry, but when we look at the surface state of a crystalline, basically you cut the crystal at some surface, and the surface, the symmetry of the surface, crystalline symmetry of the surface is different from the crystalline symmetry in the bulk. So actually, in their classification, there's one problem is that they can have some bulk topological invariant, but like inversion. But we know that all surface will break the inversion symmetry. That's a problem. So even you can identify some bulk topological invariant, but eventually you cannot find any physical consequence because not like this topological insulator. You cannot find any surface state for that. So the bulk symmetry and the surface symmetry, they will be different. So in this way, it's not so efficient to find a more realistic, like if you want to really to find some materials. So how to find that? And so here, what our strategy here is try to do in the opposite way. So we are not directly look at the bulk the topological invariant, but we try to look at the surface state directly. So basically, we try to do a classification based on the symmetry group of the surface. Okay, so in this way, because of course we derive, so basically we are looking at a semi-infinite sample, so with one surface already, and then the symmetry group of this semi-infinite system, the crystal, it's the exact symmetry when you look at the surface state, and so basically what we are trying to do here is that we are trying to look at this, try to find that whether or not this type of gapless surface state is possible in this semi-infinite system. Okay, so we try to directly look at this type of surface state. Okay, and of course now for 3-dimensional system, the brand zone is 3D, and now we are looking at the 2-dimensional brand zone basically, and try to look at what type of surface state Fermi surface can exist in this type of in the 2-dimensional the surface brand zone. And of course, this one we know that now we try to relate it to as we said already here, in order to get this type of surface state, what we require, if you think about carefully, we require is actually there are 2 type of degeneracy at this high momentum. So basically, we try to relate the degeneracy of the state in the surface brand zone to the symmetry group or the crystalline symmetry group. And actually, we have very nice tools already. We have know that because the degeneracy is related to symmetry group by this representation theory of the crystalline symmetry group. So we can have very nice mathematical tools here. Use this. Basically, we try to find the different type of representation of the space group. Okay. So here we can identify that there are three different type of crystalline symmetry which can help to protect the degeneracy and which can give you this type of non-trivial surface state. So here I just simply call it type 1, type 2, and type 3. So the first one is for the different irreducible representation. So basically, if when you have in the surface brane zone, when you have actually you need to arrange some line, there are some different different representations, and then this will give you some non-trivial state. Actually, this mirror topological insulator just belong to this class. And there's another one is that we know that is that when at some high symmetry point in the surface brane zone, when you have the symmetry operations, they will be not commute with each other. And in this case, basically, we know that there will be some high dimensional irreducible representation, and this will also give you some topological non-trivial surface state. And the third class is this anti-unitary symmetry operator. So basically, of course, the best example is transverse invariant topological insulator. And here, what we try to do is try to generalize it. We try to find that in some magnetic systems, we have this magnetic crystalline symmetry group, and that can also there's also some other the combination of transverse symmetry and the crystalline symmetry that will give you also some protected surface state. Okay. So here I will first summarize our strategy how to find non-trivial surface state. So first we will determine the two-dimensional space symmetry group, or for this semi-infinite, we consider about this semi-infinite system with one surface, and we need to identify the two-dimensional space group, and then we need to, because for the space group. It forms this brane zone, and for each brane zone, for each point momentum, and the symmetry operation which conserve this momentum will be different. We know this is known as the wave vector group, and so we try to determine the wave vector group of each momentum, and basically we try to search for the wave vector group. Search for the momentum with a wave vector group that is has higher dimension higher dimension irreducible representation, or it's more than one irreducible representation. And then we can determine the degeneracy for this high symmetry momentum, because once this moment can determine, and we know that the state at this momentum, they will be determined by these irreducible representations. And finally, we will determine whether or not it will have some possible non-trivial surface state. And then we go back so from surface state, we go back to bulk brane zone and try to obtain the bulk topological invariance. So basically, we do all things in the opposite way. Okay. And of course, there's an advantage from our approach. So basically, we can determine the surface state. We can guarantee the existence of surface state. And so another advantage is that from this way, we can very easy to use the representation theory of the symmetry group to classify different type of surfaces. So basically here, what we try to do is try to classify different type of surface state instead of directly look at the bulk state. And the third good thing is that we know that for three-dimensional space group, there are a lot. There are hundreds of three-dimensional space group. But for two-dimensional, so now we look at surface, basically it's two-dimensional surface. So it's classified by two-dimensional space group. There are only 17. So then we can very easy to get a complete study of all the possible states. Okay. And here is a table which basically shows that which type of two-dimensional space group that can have non-trivial surface state. And for this P1, P2, this file group, because it's a abelian group, there's no surface state. Actually, there's impossible to have surface state. And for this P and PG, CM, this three group, basically, one can find that this we call this type 1, basically it's something like the Miller topological insulator. It can exist. And for this PM, CMM, actually, because when you found there are two mirror symmetry groups, that were forbidden. Of course, here we didn't talk about spin, so it's about spinless fermi. And for this symmetry group, actually, there are more, both this type 1 and type 2 degeneracy we talk about in the later time, they can exist. But for these two groups, we call this type 2 degeneracy due to this two symmetry group is non-symmorphic symmetry group. Basically, non-symmorphic means there is a grad plane. And for these five symmetry group, there are some degeneracy which is due to the combination or rotation and the mirror symmetry. And so we classify into two different types of symmetry group. So next, let's try to look at each state, each group one by one. So the first state is about this PM group. So it's and PG group and CM group. So this is the most simple case. And so basically, for this group, we know that for example, let's take this PM group. So basically, it tells you that there is one mirror operation. And so for the surface Brandon, it's two-dimensional surface Brandon. Let's take this mirror symmetry operation in the y direction. So we have this, we can have this gamma to this x, this line along this red line. It's invariant under this symmetry operation. So basically, this wave vector group of this line has this sigma y symmetry group. And for this sigma y, for this group, we know that there are two 1D representation. One is basically it's characterized by the eigenvalue of the sigma y. So basically, one is sigma y 1, one is sigma y minus 1. And so basically, it's possible to have this type of surface state. So basically, is that because now you have two along this line, because you have this mirror symmetry, and then that means your Hamiltonian, basically you can block diagonal because your Hamiltonian can be labeled by this the eigenstate of this mirror operator. So when the mirror, you can have a mirror operator is +1 or mirror operator is -1, these two sectors, and the Hamiltonian will be block diagonalized from, so the hybridization between these two, they must be 0 because they have belong to the different representations of the the other state will be can be classified by this eigenstate of the mirror operator. And this is one example. So basically, now if you look at the H+, so the mirror operator is positive, then here, this example here we draw is that there are two Kähler mode. Basically, that means basically this one has, this H+ has the term number 2, and H- has -2. So basically, this is the example for the tin telluride. And of course, here, this also team, I think, is also in the audience. Okay, so this case is just about the tin telluride, so it has already been observed in experiment, and we didn't put too much attention here. And we will go to the next example. So for this PMG group and the PGG group. And basically this one here, the most important thing is that this G means the grad plane. So here we try to focus on these two cases. So of course here we know that for these two cases, basically it's related to the high dimensional irreducible representation. And actually the high dimensional irreducible, basically it's related to there's in the symmetry group, there are some operators in this symmetry group, they are not commutative with each other. So the best example we know is that, for example, for the semiconductor, zinc brand semiconductor, we know that there are this gamma 8 state which have fourfold degeneracy. This gamma 8 representation is higher dimensional irreducible representation, and this corresponds, for example, the heavy hole and the light hole in semiconductor. They are fourfold degeneracy at the gamma point, so all the state will be labeled by this irreducible representations. Okay. And so here we are talking about a special case, which is actually this two of symmetry operator. If you can find in a symmetry group that there are two symmetry operators, they are not only just not commute with each other, but also anti-commute with each other. And then what you will find is that all the state at this symmetry place, they will be double degenerate, always double degenerate. Okay. So this is the case for the most important cases for this non-symmorphic symmetry group. And so here is a simple, very simple. You can just assume that there are two operators which are commute with Hamiltonian because it's symmetry operator, but they are anti-commute to each other. It's very easy to show that they are when you look at this, the eigenstate of the Hamiltonian, all the state will be double degenerate. Here is the simple proof. Okay. And so basically here we try to look at a simple model for this non-symmorphic symmetry group. And basically we are concerned about a three-dimensional example, which is there are layered system where each has A layer and B layer. And we consider about this A layer, B layer itself is just a square lattice, but A layer has a magnetic moment along one z direction, and B layer has a magnetic moment along minus z direction, let's assume. And then we look at the side surface, okay, and then what you see is that A layer has a magnetic moment point up, and the B layer has a magnetic moment point down. And now we assume that we take the lattice that all the A layer, the atom shift by a small constant A1 along this along the x direction, and all the atom in B layer is shifted along this direction by a small constant. And then for this lattice, what you can see is that there are two important symmetry groups. So this for this surface, basically it has this PMG group. And for so there are two symmetry operations here. One is this mirror operation along this z direction. Okay, z to minus z. Let's say take this A plane, and then you will find the crystal is invariant. And another symmetry group is that another symmetry operation is this. You take a mirror around the x direction, so from this one here to here, and then the spin will also reverse because the mirror so here the magnetic moment will also reverse its direction because the mirror will change this magnetization direction, and then you shift by half of the lattice constant along the z direction. So this z direction is the lattice constant is this c here. And then you can see that this lattice set will go to this lattice set. This is just, so this operation is just the glide plane. Basically, this sigma x is mirror operator around the x direction. And this tau is half of the lattice vector translation. Okay. And now, basically, we can construct a model for this system. And now, one thing we try to prove here is that actually, if you look at the surface Brownian of this, for the surface Brownian for this xz surface Brownian for this lattice, what you will find is that the sigma z and this two symmetry operation of this lattice, they will not commute with each other. So to show that, you can simply calculate the sigma z times gx or gx times sigma z. And what you found is that actually there's one gx sigma z equal to sigma z gx plus some lattice vector. So this t is the lattice vector along the z direction. Okay. And then what you will find is that if you look at you act it on a Bloch wave function of the system. So you act this gzx, z act on this wave function, or you act this gx sigma z on this Bloch wave function. And what you will find is that for one case, because this here you have this k dot sigma tau here, and if you for the k, because this k dot sigma tau is coming from because you now have half of the translation. And now if you take the k at along this line, basically this zu line, so basically it's kz equal to pi over c line along this line. And then you will find is that these two operators actually they are minus sign before them. So this minus sign means that this symmetry operator And this symmetry operator, they will be not commute with each other, but they will anti-commute with each other. Okay. So basically, for the Broha wave function, for Broha state here, along this line, basically tell you that for these two operators, they will be anti-commute with each other. And according to our proof in the early time, basically at these 2 points, not at these 2 lines, At these 2 points, you will find, so basically as when k equal to this one and k equal to this one, basically z and u, these 2 points, all the state will double degenerate. And then, according to our early argument, so we can construct a model which has this zigzag type of surface state, and it will be non-trivial. It will be a non-trivial case. And this is indeed we write a tight band model for this system, and we try to look at we found that there will be some edge state of this system, and this surface state, and it will be gapless at the z point. Okay, so basically it's. It will be gapless, and this z point you can test that it's due to the non-symmorphic, due to this symmetry group. So the two operator in this symmetry, this sigma x and gz, these two symmetry operators both are very essential to this for this the gapless nature of this surface state. And if you can break either one, it will gap this surface state. Okay. And of course, another question is that when this, we say that this is topological non-trivial, so when you can define some topological invariant in the bulk, and actually you can go back to the bulk system for this crystal structure, and then you can define you can use this one-year function method proposed by this in this paper, and you can find that this one-year function will have some 1D number, so it's related to some topological non-trivial case. Okay. So this actually this tells us that there are more classification of the non-symmorphic symmetry group, and actually what we found is that for 2D space group there are only 4 non-trivial non-symmorphic symmetry group, and basically we found in these 3 they are possible to have double degeneracy that at some high symmetry momentum, and that means that in these 3 symmetry groups they are possible to realize non-trivial surface state. And so next thing we look at, what we look at is this, there are some this class, and for this class actually the most important thing is that they have both the mirror symmetry and the rotation symmetry, and because of fourfold rotation here is for this point group is C4V at some high gamma point and M point, and for this C4V group there are 2-dimensional irreducible representation which can give you non-trivial surface state. And this has been shown by the Bevenig group that it's possible to define some topological non-trivial state in this case, which they call they can define the topological non-trivial topology invariant, which they call the halved mirror character. Basically, is this along these 3 planes. Okay, and you can find along these 3 so on the surface is this 3 line, and you can find this type of surface non-trivial surface state. And because of time reason, I don't have time to go to detail about this thing. And actually, for this P4D group, actually it's a combination of non-symmorphic symmetry group and also this the rotation and the mirror symmetry operations. And actually, you can get more non-trivial surface state here. So now let's look at the third type of case is that this so here due to this anti-unitary symmetry operator like a time-reversal symmetry operator, and we know that for time-reversal symmetry operator the most of Y's can give you degeneracy at the time-reversal invariant momentum is because for spin force system the theta square equal to -1. It will give you this degeneracy at this time-reversal invariant point. And so here, so the question is that whether we can have some other anti-unitary operator which can give you this degeneracy, and that is true. Basically, this is given by this magnetic group. So this magnetic crystalline group, and basically in this group, it's for magnetic material. It has unitary part and anti-unitary part. So the anti-unit part here, this A is some time-reversal operator, which give you anti-unit thing, and times some rotation operator, the space group operator. So these are some space group operator. And it turned out that there is a very nice rule called the Hurling rule, which we discovered by the Wegener and Hurling in the early 30s. And they found that for there's some simple way to determine that for this this magnetic group, when you have this anti-unitary part, and how it will give you degeneracy or not. So this is so-called this Hurling rule. And basically one can use that. And actually it's very simple. Basically what you need to look at is that, essentially it's look at is that this square equal to, so this anti-unitary element, this symmetry operation, the square of it should be equal to -1, not 1. Then it will give you some non-trivial, give you some degeneracy. And so here what we look at is these two types. One is this, we call it tau theta with time-reversal symmetry, time plus translation operator. And this actually, it's possible to give you the -1. And this can exist for both spinless and spinful fermion. Actually, Professor Gilmore is the pioneer for this in 2010, and give you the example of the when you combine the translation and the time reversal, you can get some more topological state. And so here, what we look at, we also found that we also give you a model about the spinless fermion system, and we also look at the rotation symmetry combined with the time-reversal symmetry, and it will give you the, it's possible to give you some non-trivial, so this square can be to be -1, which will give you some degeneracy. Okay, so how many minutes I have? 5 minutes, okay, thanks. So here, so I will go very quickly. So basically when you do this, take the square, it's equal to the C2. Omega is for 1 for spinless and -1 for spinful. And basically if you look at the C2 representation, you have this B, you have this representation which will give you the -1 for the C2 operation. So that if the state belongs to this representation, then that means there will be double degeneracy for this state. And so basically we can construct a model, so I didn't want to go to detail about the model. So basically this model has C4 rotation times the time-reversal symmetry operation, and you can do all the things, and you can find that there will be a surface state which is protected by this symmetry operator. So I don't. And basically we can do the classification of all the possible CN theta symmetry operation, and what we found is that C2, C3 time reversal, there's no topological phase, and but when you C4 theta we have for both spinful and spinless and spinful, and for C6 theta actually we have this, we can define two topological invariant in this case. So the reason is that actually here for the C6 theta rotation symmetry we have actually in the brand zone, in the three-dimensional brand, in the two-dimensional brand zone we have 3 points, and in three-dimensional actually we have 6 points. And in this case, we can define the two topological invariant. And here is the case. So basically, we can define the Z2 topological invariant for these three. Actually, for these three surfaces here. These three surfaces, but the delta 1, delta 2, delta 3, for each surface here you can define one Z2 topological invariant. But there's a constraint because these three surfaces share some common point here, and it turns the constraint is that this delta 1, delta 2, delta 3 together this must be 0, and this so that's why actually only 2 are independent, and that's why we have two type of Z2 times Z2 topological invariant here. Okay. And actually, this can also be understood from the surface state picture. Basically, this is trivial case. There's no surface state, and this is one surface state around this gamma point, one surface around this k point, and one surface around this k prime point. So basically, these three cases. Okay. So, so here is the summary of our work. So basically, we have presented a theory to explore all the possible topological crystalline insulator, which has non-trivial surface state. And so we basically we can for free-forming system we have shown that how to use representation theory to get all the possible state with non-trivial surface state. And finally, I think because now we have shown that there are some states which didn't depend on the spin of the system. So basically, you can also generalize this system to bosonic system, and also we can generalize to the supermatic system, and as well as this well-said metal system. Okay, so this method. Thanks a lot. Yes, time reversal.
Okay, so we'll say without spin, but still have time reversal. Do you mean t squared equals to 1?
No, yes.
T squared equals 1. So
T squared equal to 1. Yeah, yes.
in the case we spin t squared minus 1. Yes. So basically, this actually minus sign not from the theta in that case, but this time reversal just give you complex conjugate basically. Yeah, it's from the rotation part basically. Oh, just the case here. Basically, for example, here, like the C4 theta, when you C4 theta just give you 1, the C4 will give you C2. C2 will give you minus 1 part, basically. For some states, this C2 will give you minus 1. Yeah. So some state like P state, after the C2 rotation, it will give you minus 1. Yeah. Yeah.
So right then, here you considered the 2D space groups and possibly the time reversal operation.
Yes.
So you could also think about, I guess, 2D magnetic space groups, as they're called. I don't know much about the 2D version of that, but in 3D, there are 1,400 something magnetic space groups. So
yes.
do you know if you do that, do you get additional things beyond these? Like, I suspect that there are magnetic translation groups in 2D that don't decompose into a product of space group and time reversal.
Yeah. This is next. We are still going on working on this thing. So now, up to now, we just look at this simple two cases. One is translation time reversal. One is this rotation time point group time reversal. We may also look at like the glide plane time reversal. What happened? In principle, we can do that. Yeah.
I think there are even others that are not quite spatial symmetry times time reversal operation. Like time reversal is mixed up with the spatial symmetries. I know that happens in 3D. I'm not sure about 2D. It's this.
Of course, it will exist. Yeah. That's the next suggestion. Yeah.
All right, we'll be good. Thank you very much.
Thank you.
Okay. It's my great pleasure to be here for this wonderful conference, and especially I would like to thank Professor Yao, the local host here, for hosting me to participate in this especially long-term program, and hopefully I can learn more mathematics and have some collaboration here. And today I would like to talk about the so-called symmetry protected topological phase. So you can think about it's something like a generalization of this topological insulator and topological superconductor but with arbitrary global symmetry G. But especially the interesting point is that we try to consider what happened for this interacting system, especially in the presence of very strong interaction. And we try to propose something called a Fermatic topological nonlinear sigma model in discrete space-time. And especially the corresponding mathematical objects we call the supercohomology theory, which can be viewed as a central extension of the usual cohomology theory. So let me just start from some definition of what is symmetry-protected topological order. First, they must have the same symmetry as any kind of trivial disorder phase. And of course, no long-range correlation. So you cannot imagine anything like a cat state, which is symmetric but has long-range correlation. And there's nothing interesting in the bulk. Excitations do not have any fractional statistics. So it's also different from fractional quantum Hall. It's indistinguishable from a trivial disorder phase if the symmetry is broken in the bulk. So just like a topological insulate, if we break this time reversal and U1 symmetry, just completely trivial. But the most important part, that it's stable against local perturbations, preserving symmetry. So this statement not really means the gap will not close if you add a perturbation, just means if you add a symmetric perturbation, there's no way to get any crossover to that trivial phase. So that's not necessary to close the gap. And as an application, the most important part is that all these kind of states, they will support this gapless edge if the symmetry is not broken. Okay, so to understand what happened for this so-called SPT phase in interacting system, I would like to prefer to start with some very simple example in 1+1D. So this is some very familiar model. It's just the antiferromagnetic Heisenberg model, and it's a spin 1. So we can add this term as well, because spin 1/2 is square, just as trivial. So this model, sometimes we call the Haldane chain. And when U equals 0, we know it's different from a disorder phase. But for a long time, we don't know what kind of phase it is. And for a long time, we just called it one-dimensional topological order. But until very recently, we realized that such kind of phase, actually, we do need to impose some symmetry to protect it. So for example, numerically, we show that like U around 1, you will have a phase transition. But if we add arbitrary perturbation, we can basically remove such kind of phase transition. But some basic symmetry you can impose to this model. For example, you can impose like either like a time reversal symmetry or spin rotation symmetry. And then we find that there's no way to remove such kind of phase transition around U equal to 1. So what's the key physics here? To understand this one-dimensional kind of phase, a couple of years ago, we developed some called a tensor network renormalization scheme to understand this so-called fixed point wave function for such kind of one-dimensional model. And it turns out if we run in this like a discrete space-time RG, and the fixed point wave function turns out to be very interesting. Although we start from some model like spin 1, we only have 3 states. Spin 1 is equal to 1, -1, or 0. But we end up with some model actually have 4 degrees of freedom. So it's like on each coarse-grained sides, we have 2 spin 1/2 degree freedom. So if you're familiar with the representation theory, we know that this representation 1/2 tensor product 1/2, basically it's just a direct sum of 0 plus 1. So it's kind of, there's an emergent spin 0 degree freedom. But this, by adding such kind of degree freedom, it becomes pretty simple. Everything decouples, so just a decoupled chain. But then what kind of thing is interesting? Just on its end, we find some spin 1/2 degree freedom. Although at the beginning, it's just a spin integer, no spin 1/2 degree freedom. So we call such kind of things symmetry fractionalization. And mathematically, the important point is that spin 1/2 just form the so-called projective representation of either time reversal symmetry or spin rotation. So spin rotation, we really need to think about it's SO3 instead of SU2, because SU2 don't have any interesting projective representation. But as a kind of a physical system, the real spin rotation is SO3, not SU2. Okay, so now I want to go to some simple example in 2 plus 1D, because 1 plus 1D, although it's interesting, but most of the problem can be solved by like a DMRG and all kind of method. But in 2 plus 1D, this model could be very challenging because in both our model, we know if there's no interaction, just some very trivial phase or symmetry breaking phase, so we don't know what kind of thing can happen. We don't have this binary structure picture. So I would like to start from a very simple bosonic example, and then try to generalize this construction to Fermion system. So let me just remind you this transverse Ising model. Maybe everyone here in physics may be familiar, but mathematician may be not so familiar. But it's very simple. This model is just a 2 plus 1D transverse Ising model. We have 2 terms. So the first term, just like parallel spin, do not get energy punishment. But if there's a spin mismatch, you have energy punishment. So this is just a transverse field, some field along x direction. So if T is 0, we get something very simple, just everything is polarized. But if T is infinity, then just kind of or every spin along this x direction. So we call this is the disorder phase, because this spin up or spin down polarized phase can be kind of spontaneous breaking symmetry. It can either spin up or spin down. But here you don't break any symmetry. Then this we just expanded the polarization along x direction as a superposition of up and down. And then we know the Guang's wave function very simple, just a superposition of all Ising configuration in an equal weight. But now we take a different look of this wave function. We think about if we flip spin here, we create a domain. So then this picture for this wave function because equal weight superposition of all domain configuration. But domain, we know it's like a closed loop. So this for any kind of closed loop, it's easy to imagine topology might emerge. So then from this wave function, we try to propose if we slightly modify this wave function by just adding a minus sign for each domain, it turns out to be a non-trivial disorder phase, just like this. Yeah, but it looks like very simple, but how can we believe it's non-trivial? So let me try to briefly sketch the proof why this is non-trivial. But before doing that, we just look at why this minus sign is interesting. First, if we put a minus sign here, it's very easy. We can still construct some exact solvable Hamiltonian, just like we just twist this sigma x to sigma x tilde. It kind of some transverse field, but with some interesting sign kind of twist. But actually, this is a 7-body spin interaction. Like if each, there are 7 spins surrounding this side here, and if I flip spin, I also measure the spin configuration surrounding it. And if they're parallel, just have contribution I, anti-parallel just 1. And you can easily prove actually every term just commute. Then such kind of nice property make it enable to solve this model. And the spectrum actually is the same as the usual transverse Ising model in the infinite transverse field limit. And the second thing is that this minus sign is something like a topological feature. And there's some local rule that we can use to generate such kind of minus sign. You can think about if I just compare some domain configuration locally, just like in this 2 configuration, I locally can deform this domain from here to here. Actually, you can think about I can cut here and regroove. So if I locally apply such kind of rule, actually it changes the number of domains. So you can slightly twist this figure. This is like, I think it's kind of try to match this symbol in the tensor category theory, but you can think about it in this way. Yeah, then if here we have 2 domains, but then you do this local move, there's only 1 domain. So it changes the number. Then we ask the question, why is minus 1? You can imagine that maybe we can have arbitrary phase, arbitrary e to I theta. But if we assume this is some kind of fixed point wave function with correlation length 0, this kind of phase will have some constraint because we can try to apply this local rule to compute all these kind of phase for the configurations. Okay, so the local rule is like this. If we think about it, we start from some local configuration here, and we want to end up with some local configuration here. But all the outside I did not plot, just means they are completely the same. Just locally, there's some difference. Then I can kind of deform this configuration to this configuration by two different ways. So in the upper pass, I kind of just kind of change the shape and the length of this domain, become like this. Then I change this, become like this. So just completely trivial, nothing happened. So in lower pass, I choose something non-trivial. I apply this local rule here. So I apply the local rule here, kind of like I cut here, I local rule. So then I have some phase e to I theta. But then here to here, just a trivial. But I just put it here because sometimes it could be non-trivial. Then I go to here. I again do this like cut and local rule. So finally end up with something here. Kind of I locally manipulated this piece. Then I find the constraint that e to I theta square must equal to +1, which implies e to I theta equal to ±1. So this kind of rule already kind of indicates there are only two possible phases, either plus or -1. Then it looks like this might be something interesting. Okay, so to make this kind of conjecture to be rigorous, I need to do something more. So try to understand what's the essential difference between these two kind of Ising disorder phase. So to make this proof, we need some technique, so-called this duality between Ising model and the Z2 gauge model. And actually in this paper on Review Modern Physics, there's a very nice introduction about this, the relation of these two models. So basically, if we think about some Ising model, start from the infinite transverse field limit, you can map it to some Z2 gauge model. So the mapping can be done through this following kind of variable redefinition. So let me explain what's the meaning of this. So suppose I have an Ising model, which on this square lattice, I have some spin. Then I can think about I have some another model, this Z2 gauge model on this dual lattice. So basically, this tau, they are spin up and down degree freedom on this link. And this spin sigma is on this plaquette center. Then this kind of relation just means, for example, if I flip spin sigma x, if I flip spin here, I kind of create a domain. So this tau is really like the domain. So when the tau spin is down, there's one domain. Tau spin is up, there's no domain. So this map also means that if I have two parallel spin, there's no domain. If these two spin, they are mismatched, there's a domain. So that's why such kind of relation will work. But we notice that such kind of relation really need this Z2 symmetry, because if I flip all the spin in the plaquette simultaneously, there's nothing change for this domain configuration, right? So that's why this kind of duality for this term to this term really need a Z2 symmetry in this model. But I put this kind of term here. You can easily to examine this term, basically just commute with this term. Because in some kind of notation, people call this model toric. But with the toric, it's a local model because gauge theory is not a local Hilbert space. So I put this term here just to make it a local. But because these two terms commute, so in the infinite U limit, if you look at the low energy spectrum of this term, just completely the same as this term. But then I can add more things. For example, I can add some kind of Zeeman field term in the in this Z2 gauge model, which will map to an interaction term in the transverse Ising model. So in other words, the kind of this standard transverse Ising model will be corresponding to these two terms. And the symmetry breaking phase in this symmetry breaking phase transition in this model exactly map to the confinement, deconfinement phase transition in this model, because in the Z2 gauge theory, we know there are two possible phases. It's a Z2 deconfinement phase and the Z2 confinement phase. So I want to emphasize that to make such kind of map possible, this global Z2 symmetry here is very important. Any term break the global Z2 symmetry, there's no way to map to there. During the 3 days of conference, we may already heard that this model actually have some interesting topological order. So let me also briefly introduce how to understand the topological order in this so-called toric model. So basically, you see this plaquette term flip order spin term, and this vortex term is a product of 4 sigma z, 4 tau z, sorry. They basically just commute. And if U and T are positive, we can try to solve this model exactly. And to make a more physical iteration, I just map this spin configuration to some string configuration. So spin up means no string, spin down means 1 string. Actually, you think about this string is nothing, just the domain in the previous model. Okay, so apparently, if U is extremely large, these 2 terms are not allowed because all these sigma z, they must be like even number of sigma spin down surround this vortex. So I remove them. So in terms of picture, it just means in the low energy subspace, when U is very large, everything just a closed loop. Okay, then this term just kind of change this shape and length of the loop. So in the end, it's very easy to see that the ground wave function just equal with the superposition of this order loop configuration. So it looks pretty similar to this other phase. You think about which is just equal with the superposition of all this domain configuration. But because the spin is live on the link now, there's something non-trivial happen. If we think about some large torus, actually, there could be ground state degeneracy, which signatures the topological order. And also, when you cut this string, there could be some end. So this end we call the electric charge. And when you have closed loop ramping some plaquette, you can also add a minus sign. And such kind of excitation we call the magnetic flux. And basically, there are 4 kinds of quasi-particles. So E and M are boson, and the bound state is fermion. And I can also sketch how to compute the statistics of these quasi-particles here. Basically, people can use this technique so-called Dan twist. Dan twist is something like you cut this cylinder, then you rotate 2 pi, then you glue back. So we can do exactly such kind of things for the 4 degenerate ground states on a torus. So let me just plot torus in this way. It looks like not good, but this inside square, this inside square and the outside square, they just identified. So it's really like a torus. You think about it, you look from the up, then you see this, and then on the bottom, it's also another boundary, then you glue them. Okay, then when I do in this Dan twist, I kind of cut here, I rotate this top, and then I glue it back. So if you only have vacuum global string, which means there's no global string, of course, nothing happened. This corresponding to this vacuum sector. And for this configuration, there's 1 string ramping around this horizontal direction. And but you cut the vacuum here, you rotate the glue back, still nothing happens. So it's still mapped to the original states. But this could be something interesting. You cut here, you rotate, then it's kind of like a string, a global string ramping around both x and y direction. So you get some new configuration. We call it 1-1. And this configuration, it's different from all the previous configurations. Then you do similar thing for this 1-1. You cut here, you rotate, and glue back. Then you can try to kind of shrink the string back and gradually go back to this 1-0. Okay, then we are able to write down this so-called T matrix, because T matrix can be computed by this Dan twist technique. Then we just diagonalize it. So it's very clear. We have 3 boson, 1 fermion. It's almost a trivial calculation. Okay, so with this kind of things keep in mind, then we think about something slightly interesting model. We call this double semion model. So it's kind of like a cousin of this toric code. So the only modification is that this plaquette term, it's not just a multiplication of all these tau x on the link, but there's also some interesting phase factor. Basically, it's like lead. The plaquette on this hexagon lattice have 6 legs. So here I use the plaquette honeycomb lattice just to try to make it closely related to the original triangular lattice model. Because these two kind of lattices, they are kind of dual graph. Okay, so with such kind of slightly complicated plaquette term, and it's easy to verify the ground state wave function of this guy. Actually, it's a kind of equal weighted superposition, but there's a minus sign modulation depending on how many kind of loop you have. Because you very large, the ground state subspace also requires this closed loop. But each closed loop could have a minus sign. Then something will interesting happen. If you compute this T matrix, you find it something like we have a minus sign here. Then you diagonalize, you find that we have 2 boson, and 2I and minus I, which we call the semion and anti-semion. So why this is a minus sign? Just look at the previous calculation. Because here we apply some local move, and if the local move have a minus sign, then when you compute the T matrix, you get a minus sign here. So the conclusion is that this model have very different quasi-particle statistics. Okay, but although this model have different quasi-particle statistics, overall it's still a Z2 gauge theory. And we can think we are still able to map it to something like Ising model, but some twisted Ising model. So let us do this map. Okay, so again, this domain spin, we call it tau, can be represented as a product of this sigma. So the sigma spin now lives in this plaquette center. So they basically form this triangular lattice, the model I proposed at the very beginning. And also, if I flip this sigma spin, which like apply sigma x, then I need to change the spin configuration along this plaquette. So that's why here the map like sigma x is a multiplication of all the tau x on this plaquette. Okay. Now you can see this model exactly can be mapped to this model. And this Hamiltonian indeed is non-trivial or twisted Ising model I proposed at the very beginning. And so far, we know there's something interesting twisted Ising model, but how to prove it? There's no way to connect this kind of ground state, the ground state of this model to the trivial Ising model. So proof is in the following way. For any kind of Hamiltonian preserving Z2 symmetry, for example, we can put alpha here. So this is the simplest Hamiltonian we can think about. If alpha equal to 1, just the trivial Ising model, transverse Ising model in the infinite field limit, and alpha equal to 1 equal to 0, just this twisted model. And then we can map to this side. But this side, we know that when alpha equal to 1 and 0, there are 2 different topological orders because these quasi-particle statistics are very different. So the belief is that without phase translation, there's no way to change the statistics of the quasi-particle. And I think this part Xiaogang also mentioned in his talk. That means because these 2 models basically in the U infinite limit, you look at this low energy spectrum, they are completely identical. So here, there must be a phase translation. Also imply here there must be a phase translation. Or you can think about opposite. Assume here there's no phase translation, then imply here also no phase translation, which is a contradiction. So now we basically prove this kind of non-trivialist of this model. But actually, in terms of this principle, you can think about it in some slightly different way. You can think about for any global symmetry, let's assume it's a unitary symmetry. You can always couple to some background gauge field. And then it's possible to ask what's the breeding statistics of this gauge flux. It turns out this non-trivial Ising disorder phase, if you compute this breeding statistics of the Z2 gauge flux, it's a semion. It's not a boson. That's kind of response, which clearly identical to different SPT phases.
But because of the isomorphism, you find a quantum circuit that takes that implements this change of coordinates and twists the Ising model from normal to twisted.
Yeah, to the twist to untwist, you can relate them by some local unitary that breaks this global symmetry. Yeah.
So the point is the Z2
Right. Okay, so let me just briefly make a conclusion. What happened for the bosonic model, and then I can move to the fermionic model based on a very similar principle. So in 1D, we almost know everything just classified by this projective representation on the boundary. And in 2+1D, based on Digraph-Witten's theory like 20 years ago, we know that all these breeding statistics for a gauge theory is just classified by this third cohomology class. Actually, in their original paper, I think they write down it as H4 BG with coefficient Z. But this happened to be identical to G with coefficient U1. Then it's easy to conjecture that this kind of thing might also work in high dimension. And indeed, in 3+1D recently, Michael Levin's group, they proved that this flux line can have non-trivial braiding, which happened to be classified by this fourth group cohomology class. And now we have came up with a kind of concept that this group cohomology class actually can help us to construct some non-trivial topological term.
So how does your classification compare to Cheng line and center?
I think for the bosonic piece, they claim there's something beyond this group of cohomology, and Kapustin also have a paper about this cobordism. Yeah, but here I'm not. Yeah, they have a single example with time reversal symmetry. Yeah, yeah, but so far we only know one example. Yeah, yeah. But here I just try to make this kind of construction. I'm not claiming it's complete or not. Yeah. Okay, so the construction is following. Basically, you can think about this partition function for this kind of SPT phase can be generated by this Hamiltonian, because we already have some exact solvable Hamiltonian. But you can think about the partition function just z exponential minus beta h, but you can then take the limit beta to be infinite. And because this is topological invariant fixed point, actually you can define the partition function on arbitrary triangulation. So here, this scheme, just like in 2+1D, we first have a tetrahedral. And on this tetrahedral, we associate with something called a branching structure, like on each triangle, we don't allow this oriented loop. So branching just means a kind of arrow on this link. Then such kind of trick can make this tetrahedral have a local ordering. Like here, we don't have any incoming edge, but here we have 3 incoming edge. Then this function does not necessary to have a cyclic symmetry. So basically, the partition function is very easy. Just a multiplication of all these kind of U1 function on this tetrahedral. And it's divided by some normalization factor. So here is the order of the group. And NV is the number of vertex. And basically, this what we call the new D+1. It's called it's actually it's a co-cycle in this group cohomology class. So basically, it's like a G cross G cross G kind of multivariable function mapped to this U1. So in 3+1D, we have 4 group elements. So there are 4G. Okay. Also, because it's a nonlinear sigma model, so we require this G action is trivial. Basically, you apply G to every group element, just nothing change. And importantly, this so-called co-cycle equation, sorry, should be good 1. Enforce this kind of topological term is topologically invariant. And once we have this condition, we can systematically kind of construct the generalization of this Z2 SPT phase and the corresponding exact solvable Hamiltonian in arbitrary dimension. And let me just briefly sketch this kind of picture in 1+1D. For example, in 1+1D, we have some triangle, and this partition function just multiplication of some triangulation. And this nu2 depends on 3 group elements, and it's just a U1 function. And this kind of co-cycle condition just evolve 4 nu2. And geometrically, you see, if you match each nu2 with a small triangle, it's nothing, just a retriangulation. And I would like to mention there also it's a SIJK, and which basically related to this orientation of each triangle. It could be take a plus or minus. Then we also have this very simple holographic principle. If we want to construct this ground state wave function, we just put the one group element in the inside. So the ground state wave function basically can be viewed as a kind of partition function with a boundary. So on the boundary, you just associate it with this physical degree freedom. Here, I just label it by use these group elements. So for Ising model, just like up or down. Then you just can express this ideal ground wave function in such kind of form. Okay, so all these things looks like pretty nice for bosonic system, and we're looking for generalization to Fermion system.
How do I see that for the discrete that you are minus 1 to domain 1 number using this general wave function?
Yeah, so in the domain picture, you need to choose some so-called co-boundary. Sorry, I forgot to mention. So not each new tool satisfies the co-cycle condition corresponding to a different phase, because different new tool, they can be related by so-called co-boundary. And turns out, if we just two new tools just different by co-boundary, they belong to the same phase. The spreading statistics does not change. And if we choose some proper new tool, proper new with a proper co-boundary, you can recover the previous picture. But if we don't, you just choose some arbitrary, then it's not so nice. Yeah.
I'm confused though, sorry. I thought the Z2 model was intrinsic topological order. This is SPT. So
Yeah.
The other one is also SPT. It's not SPT due to another intrinsic topological.
Yeah, yeah.
I think the gauge theory formulation is SPT.
Sorry.
In the dual gauge theory, it's SPT, and in one formulation, it's
No, this SPT due to a double segment gauge theory.
yeah.
It's due to a topological, but itself is SPT.
Yeah.
The fixed point wave function is a function of what data?
A function of this new. Just once you have this new, you can.
It depends on the G in the center. It's a function of that G.
It's independent. It turns out it's independent. You can choose arbitrary G in the center. Because it has this symmetrical condition, you can always choose this as trivial. Because here, in this step, you see that this kind of retriangulation, you can freely remove this G0.
It becomes a function of the ket. On each plaquette, you end up having assigned a element in complex numbers.
Yeah. Yeah, so actually for writing in Fermion system, such kind of concept is still very useful. Basically, we think about this breeding statistics and all this discrete space-time nonlinear sigma model. We can still do this parallel way. And it turns out if we do this, we find something very interesting in mathematical, something called a supergroup cohomology, which is a central extension of this normal group cohomology theory, or in some sense, we can say it's a square root of that. I can show you why. So again, we just start from some very simple model with Ising symmetry, Z2 symmetry, but for Fermion. So for Fermion, we can do more things, because for spin model, the global Hilbert space is just a tensor product of some local Hilbert space. But for Fermion, what we need is a Fock space. So to construct some Fock space, the simplest way is also we put some Fermion degree freedom in the triangle. So now you can think about this total Hilbert space has included both boson and fermion, but the fermion lives in this triangle, and the boson lives on the site. Now we can consider some interesting disorder phase. But this disorder phase is slightly different from the bosonic case, because we want to also have some fermion degree freedom. So basically here, I just kind of decorate some fermion. So the fermion either on the top or on the bottom. Like here is 1 and 2, I create a pair of fermion. Here I create a 4 pair. And in such kind of rule, you find that this alpha can take some square root of -1. Now it's allowed to take this plus minus I. So I can explain why. First, we can think about some rule how to decorate this domain. Because it's a topological fixed point, the kind of lattice symmetry is not important. We can assume this some direction from down to up is special. Then with respect to this reference direction, we think about this string and this class of string and this strings, they are kind of something topologically different. Because you think about if this special arrow induce some orientation on this string, it just goes through. But here, these two arrows, they just match. So this topologically, they're different. So it's possible to decorate with some fermion. And once we pin down such kind of decoration rule, we can further think about what's the local deformation rule. Of course, it's similar like this Bosonic case. We expect some generic phase factor alpha should be here. But now slightly complicated because if I rotate these legs, there could be two different cases. In this case, compared to this one and this one, I create a pair of fermion. But for this case, I don't kind of create so the fermion number is the same, just like one fermion hop from here to here. Okay, so with such kind of rule, we can further examine this consistent condition as for the Bosonic case. So kind of I start from some local domain configuration like this, end up with this. Then I do in the first pass, just kind of almost trivial, just hop some fermion from like 1 to 4, 2 to 1. But the lower pass, I apply this local move. But interestingly, for this upper pass and the lower pass, they kind of differ by one fermion exchange. Because when you are doing this upper pass, it's very trivial, just like two-step. You annihilate C1, create C4, annihilate C2, create C1. But if you do the lower pass, you have alpha square, but you first annihilate C2, create C3, and annihilate C3, create C4. But because in the vacuum, there's no C3, so you can just simply remove this part. But here, it's also kind of, in the vacuum, already have C1, so you can remove this C1 dagger C1 by exchange C1 dagger to here. Then you end up with something like this. But this, there's a fermion sign. And it turns out that this alpha must equal to plus minus I. So that's the interesting thing that this kind of fixed point structure can be twisted by this fermion statistics in the so-called fermionic SPT model. Okay, so we can further do more kind of detailed calculation, and we can actually exactly show the exchange phase of this Z2 flux here. It's not a semyon. It's kind of it's half of a semyon. It's kind of pi over 4 annual. If I change the phase for 2 semyon, I get this phase pi over 2. But here, it's pi over 4, plus minus pi over 4. So it's like a square root. Okay, so with this kind of picture, we are able to go some general case. And to control the general case, we again want to control this nonlinear sigma model in discrete space-time. But now we have the very nice picture because we know this wave function just like a partition function with a boundary. So you can think about on the boundary, I do some triangulation. So with this triangulation, it's really like a wave function, right? But because in the wave function construction, I put some fermion degree freedom in the triangle. So you can think about in the partition function, it's also very natural to put some fermion degree freedom on this triangle, like on the face. Yeah.
So to that fermion SPT, so is that so does that correspond to free fermion SPT?
Yeah.
So
Yeah, for the Z2 case, actually, free fermion have a Z classification, but then it collapses to Z8. So this is belong to this. This is D plus ID. Yeah. You can compute this phase. So P plus IP is pi over 8. So here it's kind of double of that. Yeah. Okay, so this partition function, the slightly complication is that we need to attach some fermion. But in path integral, it's more familiar that we use this Grassmann variable kind of attached on the face. We not only define some U1 function as some kind of function of this group on the vortex, but also there's some fermionic degree freedom on the face. Okay, but this face we have some N2. So N2 valued on just 0 or 1 just means for some given group element, there could be some rule. So in the previous example, just a decoration rule. Whether we should put a fermion here or not, completely determine whether this function is 0 or 1. If it's 0, just means theta to 0, nothing. And 1 means we attach a fermion. And we consider a simple case. This global symmetry, just some Bosonic symmetry tensor product fermion parity. Of course, in general, we can have more complicated symmetry, but I would like to start from the simple case. Okay. Then you can think about this construction can be generalized into arbitrary dimension. Basically, we have a D simplex, but on the boundary of D, on its D minus 1 simplex, it's always possible to attach some fermion. And with this kind of branching structure, this boundary always have orientation. So orientation plus, you put a theta, and orientation minus, you put a theta bar. So it's very natural the fermion appears in pairs. You can think about this fermion declaration rule to make this amplitude local. There's a constraint that you sum over all this fermion number on this surface must always be even. So that's a locality condition. Otherwise, each local piece, it's not a local kind of TKFT. Okay, so there's slightly more detail, but because it's late, so I just try to jump this piece. So actually, when you define this partition function, you need to put some minus kind of weighting function. And this m is kind of, you can express m in terms of d. Once you have, for any given d, you can express it in terms of m, because this sum over nd is always even. So such kind of expression is possible. So m is also valued as 0 or 1. But with such kind of partition function, we can show the topological invariance if we impose the following so-called super Kozakian condition. So the interesting thing is that now we find that the multiplication of all these things, it's not a 1. Kozakian is something kind of, you just remove one group element and you doing this alternative like multiplication, end up with 1. But here something non-trivial. It has a sign. Sometimes could be 1, sometimes could be -1, depending on the value of all these group elements. And there are some more detailed things, but basically this F4, for example, in 2 plus 1D, just a couple product of this 2 N2. And N2 basically, we call a graded structure. It's just valued in this GB with Z2 coefficient, because it's just kind of valued as 0, 1. So naturally, it's Z2. And the function FD plus 2 turns out to be the very novel kind of mapping between different cohomology class with Z2 coefficient. It's called a stimulus square. Actually, Professor Michael told me this story because I just bring my paper to him and ask him, oh, what's the meaning of this very complicated kind of sine function? He told me, oh, that's a stimulus square. Yeah, so that's very nice. And finally, we understand that this is a function just a mapping from h upper d to h upper d plus 2 with Z2 coefficient. So actually, this kind of things guarantee some consistent condition of this grading structure. So yeah, let me just with this kind of conclusion. So basically, because in the previous kind of twisted cohomology class condition, we do need to have some constraint for this graded structure. Now, usually think about it, you can pick up an arbitrary thing, but it's incorrect because on this side, it's like a co-boundary in HD plus 1. It's a co-boundary in HD plus 2. But therefore, this part also must be a co-boundary. So that's why this graded structure actually should be some subgroup of H upper D, GZ2. Yeah, it's a subgroup. So such that it's what we call the obstruction-free subgroup. And with such kind of graded structure, it's kind of valid. Then we are able to make a central extension of this original bosonic cohomology class, which is kind of like a normal subgroup. Actually, there's slightly more detail in 3 plus 1D. Sometimes you find that when you embed this bosonic SPT phase into fermionic SPT phase, they just become trivial, they collapse. The reason physically because this fermionic local unitary is more general than bosonic local unitary. If you transform them in terms of bosonic languages, it have a string, have some sign, it's not really local. So that's why here will collapse. So the very good example I will show you later. It's a class protected by time reversal symmetry. Okay, yeah, so this is almost a final slice. So basically I can show you some example. So the most interesting example is in this 3 plus 1D with time reversal symmetry t squared 1. And actually it turns out in the bosonic case, I think Danfried also mentioned the classification Z2 square, and Santi also have the work mentioned there's one example beyond the cohomology class. And all these bosonic SPT, they just become trivial, which means the center here, if we input this Z2T, then the center just completely trivial. So the only non-trivial thing is this graded structure. Yeah. With such kind of non-trivial graded structure, we are able to find some SPT phases that are beyond the K-series classification and also beyond the bosonic SPT, because this kind of symmetry class, if you input it in the K-series classification for free Fermion, you just get nothing. But also, if you think about the bosonic SPT, you know all of them collapse. You also get nothing. But here we do find something new. Yeah. Okay. So we currently have something in progress, kind of in 1+1D. We know this special super cohomological class construction is complete, but it's still actually incomplete in 2+1D. And Cheng also mentioned with Ising symmetry in Fermion system actually have 8 phases. And currently we only find Z4, the 2 bosonic one and the 2 fermionic one with ± I coefficient. Actually, you can